All right, welcome back, everybody. Today we're going to be doing section 7.8, which is about improper integrals. This is actually one of my favorite sections because it gives us a little bit of a taste for what the work we'll be doing will look like when we get into chapter 11, which I talk about a little bit at the end of the slides. So let me go ahead and get started. I'll pull up the slides, and here we go. All right, so this is actually the last section of chapter 7 that we'll be doing. Oh, I didn't mention it before, but we skipped section 7.6. That's basically just doing integration using a table of integrals that are given in the back of the book. So that section is pretty much just, hey, do you recognize this pattern in the integrand? Then look in the back of the book. There's a table of some common patterns. Use those formulas and compute. That's pretty much it. So we tend not to cover that section. All right, but here's the overview for this section. We're going to talk about two different types of improper integrals. Integrals over infinite intervals, and then integrals with discontinuous integrands. All right, then we're going to learn a few tests. We are going to prove a couple of these tests. We're going to learn two different p-tests. That's what they're called, the p-test. And then we're going to learn a very important test called the comparison test for integrals. All right, so here we go. What is an improper integral? Well, so far when working with definite integrals such as this, we've had two implicit conditions that we've required but we haven't said out loud. The first one is we require that the domain of integration is finite. In other words, one of these endpoints, quote unquote, it can't be infinity. So we've specifically required that a and b are real numbers and that our domain of integration is finite. That's one thing we've assumed without saying it out loud. We have also assumed that our integrand is finite. In other words, our function is bounded, or I shouldn't say bounded, I apologize. Our function is not, actually, yeah, that is what it means. Our function is bounded on the interval a to b. This basically means that there aren't any infinite discontinuities. So for example, let me draw a quick picture here. Like if this is a and this is b, we have not looked at situations where our function might look like this. Maybe there's some point c where there's an infinite discontinuity, right? We've implicitly said you can't do that. All right, can't do that. And that's one of the examples we're going to work with today. We're going to explore how to deal with integrals of functions that have a discontinuity in that interval. So those are the two types of improper integrals, ones that have an infinite domain and ones that have a discontinuity. So, oh yeah, so if either of these two conditions are not satisfied, the ones above here, then we have what's called an improper integral. It is an improper integral because it is not, doesn't fit the conditions of a standard Riemann integral in order for us to compute an integral or evaluate it or even investigate it. So the thing is, though, that these improper integrals may still be evaluable, and we can approach their value or think about how to find their value using the area so far function and limits to investigate them. So once again, limits play a critical role in everything that we do in calculus. All right, so let's look at type number 1. We'll go through the definition, make sense of it, and then we'll see how to work with them, all right? So here's the setup. This is the integral that we want to evaluate, the integral from a to infinity of f of x dx. Well, if this integral exists, the integral from a to t, for every number t greater than or equal to a, then we can define this improper integral as the limit of these definite integrals, provided that this limit exists as a finite number. Remember, that's always the case with limits. You cannot use this type of equation or state this kind of a definition if the limit does not exist, right? Or if the limit is infinite. So there's a couple things we're requiring. We're requiring that these definite integrals all exist for every number t greater than or equal to a. And if that's the case, then what we can do is we can define this improper integral as the limit of these proper integrals. That's basically the idea. And you can also go both ways. So it doesn't just have to be a to infinity. It could be another integral that goes from negative infinity to b, for example. What do? Well, as long as these definite integrals exist for every value of s less than or equal to b, then we can define this improper integral to be the limit of these proper integrals. Why is this so handy? Because we know how to deal with these types of integrals, because these types of integrals are just definite Riemann integrals, and we can use all the techniques that we had in the past on these things. Again, this limit has to exist as a finite number for us to be able to do this. All right, now you can even have both cases. So you can talk about an integral that goes from negative infinity to positive infinity. You're just going to use two separate limits, all right? But there is, again, another catch, another catch. These integrals have to exist for every number t greater than a, or greater than or equal to a, and this integral has to exist for every number s less than or equal to a. So what you're really doing is you're taking this infinite interval, you're choosing a point in the middle somewhere, wherever you want to choose it actually, and then you're splitting the integral up. And as long as these limits exist, you can do this splitting. That's the one catch. That's what I say right here, provided these limits exist as finite numbers. So if one of these limits is not a finite number, all bets are off. You can't split it up in this way. But I want to say this here, that number that you choose in between negative infinity and infinity is your choice. You can actually choose whatever number you want. A lot of times 0 is a good choice because 0 is, kind of in the middle, you could say. But that's basically the idea. If you've got an improper integral, turn the bound that is infinite into a t or an s, and then use limits instead. So here we go. Oh, wait, before I do that, yeah. So what another definition here. These improper integrals here and here, they're called convergent if the limit exists as a finite number. So if that does give you a number, we say that the integral is convergent. Otherwise, we say it's divergent. So convergent means you're getting a finite number. Divergent means you're not. You're either getting infinity or you're getting nothing. Doesn't exist. Kind of makes sense, right? These are limits, so you can talk about convergence and divergence, or existence in some sense. All right, so here's how we do it. Let's consider the function 1 over x squared. Classic function. This is one that you should have memorized. You should be able to see the picture in your head when you see it. And let's just consider the region A that's under this curve and to the right of the line x equals 1. So in particular, we're looking at the area of this region. I guess maybe I will draw a quick sketch of it up here. Here we go. This is 1 over x squared. Here is 1. And this is the area that we're looking at. So one of the things that I love about this particular section is the interval is infinite, right? The interval is infinite. So this keeps going, and there's infinite, there's, how do I say it? I can't say infinite area because it may not be infinite area. And that's what's so funny about this. Even though there's no end to this curve, the area underneath the curve could actually be finite. It may not be infinite. So you get to play with infinity in a lot of interesting ways. It's one of the reasons I love calculus so much, because you get to play with infinity. How often do you get to play with infinity, right? So if the area under here, that red area, is finite, then we can define this integral to be that area. So again, if this exists as a finite number, then we can say that that integral is that value, that area. But it may not be finite. That's the catch here. Dealing with improper integrals, you're not guaranteed that the integral will be finite or even exist. So you have to be very, very careful. May not be finite. How do we do this? Well, instead of taking infinity to be the upper bound, we're just going to call an upper bound t. And we're going to let t be any number greater than or equal to 1 but less than infinity. And when we do that, we can define an area function, a of t. This is that area so far function that you talk a lot about at the end of Calc 1, the area so far function. So the area so far function is the area under this curve from 1 to t. That's what it is. Good news is that is a definite integral. This interval is finite. It's the interval from 1 to t. There's no improperness going on. It's just a standard definite integral, and luckily this function is simple enough that it has an elementary antiderivative, and you can just do FTC2, and boom, you're done. That's what we do here. Antiderivative of 1 over x squared is negative 1 over x. We evaluate it from 1 to t, and we get 1 minus 1 over t. So that is the area underneath this curve from 1 to t. We have a formula for it, formula for that area. That area is finite, right? That area is finite because our function is bounded on that interval. The interval is finite, and so that area is finite, and this is a well-defined function. So for each t, you get a specific area. Now what we're going to do is we're going to take the limit as t goes to infinity of this area so far function. That's the next step. So the limit as t goes to infinity of this area so far function is the limit as t goes to infinity of that. When t goes to infinity, this value goes to 0, and so we're left with 1. So as wild as it might sound, the area under this curve from 1 to infinity is the limit as t goes to infinity of the area under these curves. But the area under these curves is given by this, and we just found out that that limit is equal to 1. So the area under this curve is equal to 1. That's right. The limit is finite. The integral is therefore convergent, and it converges to the value 1. So maybe if I flash back to this picture, you might want to just ponder it and think about it for a minute, actually. Here, I'll throw that up for just a moment here. Boom, there we go. What I'm saying is that this area under here is not only just finite, it's actually equal to 1. Just 1. All right. Wild stuff, huh? I think it's fun. Okay. Now, where were we? We just did this. Just did that. Let's talk a little bit about this. So, one thing that I notice students tend to forget at this phase is how important the limit operator is. So, I just want to really emphasize here the importance of using that limit operator. This thing right here, right here, right here, and then when we take the limit, we get a value. You cannot omit these limits. So a lot of times students will, for example, say, oh, can we just pretend this is some number and just compute the integral and plug in infinity? No, you cannot do that. You cannot do that. This thing doesn't even have a definition without this limit operator. Like you must have that limit operator to be able to talk about what this symbol even represents. So it's very important that you understand that this symbol is talking about a limit. It's a limit of numbers. It's a limit of finite numbers. And if that limit of finite numbers converges and goes to something, then we can talk about what the actual value of this integral is. So it's very important to use the limit operator and to use it carefully. I'll just reemphasize this. Remember that a definite integral is just a number. So these things right here are just numbers. That's all they are. And we're seeing where these numbers go. Where do they go? They go to 1. So that means that this thing has to be equal to 1 because that is the limit of those numbers. Yeah, and what we're doing is we're taking the limit of these area functions as t goes to infinity. So you must use the limit operator, and you must use it correctly, appropriately, and carefully. Just wanted to say that specifically. All right, let's practice here. So let's evaluate this double-sided improper integral if it even converges. So I want you to try this one on your own by splitting it into 2 separate limits and then calculating each of those limits. One hint I'll give you is that this one will actually converge. So it is valid to split it into those 2 limits. But I want you to think about that for a minute first. And then say something out loud to yourself about what you would do first. What do you want to try first? All right, now try to work it out on your own. Use the limit operator properly, correctly, and see if you can evaluate what this is. What does this integral converge to? All right, now let's do it together. Here we go. First thing we're going to do is we're going to rewrite these infinite endpoints as limits instead. And because we've got a double-sided improper integral, we can actually pick any number we want in between negative infinity and infinity to be our split point. I chose 0 because 0 is a good number to choose. And now these are definite integrals. So these are definite integrals. Our function is bounded on these intervals. So these are finite numbers. We just have to compute what those numbers are. And we can do that using FTC2. So here we go. We're taking the limit. We're taking the limit. This is actually the, what is it, antiderivative of arctangent. So this becomes this. This becomes this. Now we can apply FTC2 and we get these two values. This is another reason why it was good to pick 0, because arctangent of 0 is just 0. So that disappears, and now we're left with these two limits. But now this is one of those times where I want to remind you that we really, really love arctangent. And we love arctangent because arctangent is bounded. It's a bounded function. So the limit as s goes to negative infinity of negative arctangent is negative pi over 2. And then the limit as t goes to infinity of arctangent is pi over 2. So this limit is pi, all right? And so that means that the area under this curve, this infinite curve, or sorry, the area under this curve on an infinite interval is pi. Pretty cool stuff, right? Pretty cool stuff. It's pi. Maybe not so unbelievable if you kind of think about the picture. What does arctangent look like again? Well, let's see. If x is 0, we get 1. And then as x gets very large, it gets smaller. Arctangent looks kind of like this. So we just computed the area underneath that curve. And we found that that area is pi. Cool stuff. So even though the interval is infinite, the area is finite. Amazing stuff. Okay, so let's talk about the p-test. So we're gonna learn a few p-tests in this class. Right now we're just doing p-tests for integrals, and we're gonna do the p-test for integrals over infinite intervals. All these in and ins, right? Integrals over infinite intervals. There's a tongue twister for you. And this is a nice test because it automatically tells us the convergence or divergence of certain kinds of integrals. So here are the integrals we're looking at. This right here is called a p integral. It's called a p integral because it's just 1 over x to the power p. This theorem, only applies to integrals that look like this. So I want to make that clear before we look at the result. This theorem does not apply unless your integral has this structure. This has to be 1, this has to be infinity, it just has to be 1 over x to the p, and if you have that scenario, then you get this conclusion right here. And the conclusion is nice. It turns out that this integral is convergent if p is greater than 1. So if this power is like 2, 3, 4, 5, 6, 7, 8, 9, anything like that, the integral will converge. It'll converge. And the integral will diverge otherwise. So if this power is, if p is equal to 1 or 0 or -1, -2, it doesn't even have to be integers. That's the best part. P can be any real number. But if that real number is greater than 1, this thing converges to a number. And if that real number is less than or equal to 1, it diverges, and you will not get a finite amount. So even better than that, we can figure out what it converges to. So when it does converge, when p is greater than 1, the integral converges to this value, 1 over p minus 1. 1 over p minus 1. That's what it is. In fact, maybe now let me flash back to a previous example we did, this one. This one right here. Remember this one? This is a p integral. Notice that the lower bound is 1, upper bound is infinity, 1 over x squared. This is a p integral, and so we can apply the p-test. The p-test says, hey, look at that exponent. If that exponent is bigger than 1, your integral converges. Not only that, it converges to 1 over p minus 1. So just by looking at this integral and using the p-test, I can say that this converges, sorry, handwriting's bad, converges, and it's going to be equal to 1 over 2 minus 1, which is 1 over 1, which is 1. And lo and behold, that's exactly what we got. We got that it was equal to 1. So the p-test is great. If you've got a nice integral, if you've got a good old p integral, it tells you all you need to know about it right up front. All right. This one we are going to prove. So we're going to go through the proof of this right now. And we're going to split it into cases to do so. We're going to choose p equals 1, and then p does not equal 1. So starting with p equals 1, we get this. 1 over x to the p just becomes 1 over x. And now we have this integral, and we can basically do the same thing we did before. We can look at the limit as t goes to infinity, and then see what we get. So remember, the antiderivative of 1 over x is ln of x, or I should say ln of absolute value of x, but because these numbers are all positive, we just get ln of x, like so. And then we get these two things, and the limit as t goes to infinity of natural log of t is infinity. So it diverges. So we've just proved that the integral is divergent when p is equal to 1, just like so. All right. Now let's do when p is not equal to 1. So when p is not equal to 1, this is what our limit calculations are going to look like. So let me just walk through here. 1 over x to the p is x to the negative p. We're going to introduce the limit operator so that we can deal with definite integrals instead. This we can apply FTC2 to. So the power rule for antiderivatives says that this will be the antiderivative, and we're going to evaluate it at these two numbers. So when we simplify things, we get this. What I'm doing to go to this step is I'm pulling out 1 over negative p plus 1 and pulling it out of the limit. Remember, p is a fixed number here. P is a fixed number for these purposes. We're choosing a fixed p, so we can pull that out of the limit. Plus, the limit only cares about stuff that has t involved, right? So now what we can do is we can use FTC2, we can plug in t, we can plug in 1, take their difference, and we get this, right? Yes, that's right, x equals t, x equals 1. All right, so now we end up with this. So t to the negative p plus 1 minus 1 to any power is 1. So we get that. Now I'm going to rewrite this like so, just to kind of emphasize what's going on. So for now, let me pull things together for a sec. This integral is equal to this limit. That's where we're at right now. Now we want to investigate what this limit is when p is greater than 1 or negative 1. I'm sorry, greater than 1 or less than 1. That's the next step. So here we go. If p is less than 1, then that means that p minus 1 is less than 0. That means that this exponent right here is negative. And so because this exponent right here is negative, it's kind of moving this whole expression to the numerator so that t is in the numerator. But that means that this thing is going to go to infinity as t goes to infinity. Because you're basically going to end up with like t to the k minus 1, where k is a positive number. And then you take the limit as t goes to infinity, and the whole thing goes to infinity. So it diverges. So if p is less than 1, it diverges. And now we've proven that case. Now let's look at the other case. So now if p is greater than 1, then p minus 1 is greater than 0. And so that means that this exponent is already positive. So as t goes to infinity, this term goes to 0, and we're just left with negative 1. So that's this calculation right here. Now we can take this limit. This piece is going to go to 0. And so we're left with negative 1 over 1 minus p, which is 1 over p minus 1. And the integral converges to that value. Ta-da! Pretty cool. I think that's pretty cool. P integrals. So we've got p integrals, we've got the p-test, super, super handy. All right, now let's talk about the other type of improper integral that we're going to explore today. So we're going to look at improper integrals of type 2. These are integrals that have a discontinuous integrand. So in this case, what's happening is our interval is finite, but our function has a discontinuity on that interval. So here we're saying if f is continuous on this interval, but discontinuous at b, then we're going to do the same kind of technique. We're going to take this improper integral and we're going to rewrite it as a limit of proper integrals. So maybe if I can draw a quick sketch right here, maybe pretend this is A, pretend this is B, and maybe our function has an asymptote right here. Maybe our function goes like this, right? Question is, what's the area underneath? What's the area underneath? Well, it's improper because the the upper bound, you could say, is not somewhere where the function is defined. So for example, you can't use FTC2 because the function is not even defined at that point. So its antiderivative is not even defined at that point. And so you can't use FTC2. How do you get around that? You be clever and you use limits and then you work with definite integrals. So here, we're instead going to choose t to be any number that is less than, or sorry, any number that's less than b. I probably should have written that in here. Hold on a sec. I'll say this, t is less than b. There we go. And we're going to look at the limit as t approaches b from the left. So we're basically going this way with our limit. Now, the integral from a to t is a definite integral. Our function is bounded on that interval. The interval is finite. We can use FTC2, hopefully, if we've got a nice function, and no problems. So what we're going to do is we're going to look at the limit of these proper integrals, and that will be what our improper integral is. All right, so part B here is the same thing, but maybe your discontinuity is on the other side. So now instead of the asymptote being here, maybe the asymptote is actually here. How do you deal with that situation? Same idea. You basically just take the limit as you approach from the other side. That's it. Approach A from the right instead, and that's what's happening right here. Now, if you've got a discontinuity within an interval, so let's say you've got a function that's defined on A to B, the interval A to B, but it's got a discontinuity in the middle. How do you deal with that? You take the limit as you approach that discontinuity from both sides, and if both of those things exist as finite numbers, then you can split up your integral into that sum. So it's just like we had before, except now we're not going out to infinity. We're approaching some number where our function might go whoop, might blow up, or go down to infinity, or maybe even do something like this, right? Anything like that. Or it could even just have a jump discontinuity. It could even have a jump discontinuity in there. But those are easy to work with. Jump discontinuities aren't so bad. It's the infinite discontinuities that make things a little bit weirder. Because jump discontinuities, you still have boundedness on either side. Okay, so those are the improper integrals of type 2. Just like before, we've got a definition of convergence. So if those improper integrals exist as a finite number, then we say they are convergent. Otherwise, we say they are divergent. So let's try this one. This one I want you to try to do this one on your own, and then we'll work on it together. So look at this one and see if you can evaluate this integral if it converges. Think about it for a minute first. All right, now say something out loud about how you're going to proceed. What are you going to do first? All right, now try to work it out on your own, and then we'll do it together in just a minute. All right, here we go. Let's do this one together. Let's see. Okay, so one thing I noticed by looking at the integrand is that we've got a problem when x is equal to 2. If x is equal to 2, then we have 4 minus 4, which is 0. So we've got an infinite discontinuity at the endpoint. We've got an infinite discontinuity when x equals 2. So that means we do have an improper integral of type 2, and we're going to have to take the limit as we approach that discontinuity. Excuse me. Yeah, so the integrand's discontinuous at 2, so we're going to take the limit of these proper integrals instead. Now, this integral is not so hard to evaluate. This one we can use a substitution to evaluate. Let u be 4 minus x squared. Then du is equal to, typo. I'll fix that later too. 2x dx. There should be a 2x right there. 2x dx. Yes, 2x dx, actually negative 2x dx. There we go. And then remember, because we have a definite integral, we need to change the bounds. Yes, you need to change the bounds. Yes, you need to change the bounds. How do you do that? With the literal substitution that you choose right here. So when x is 0, u is equal to 4. And when x is t, u is equal to 4 minus t squared. Thus, this integral can be rewritten like so. This one can be rewritten like this. There we go. We still have this limit. So remember, we converted this into the limit of proper integrals. So that limit operator is still there. All we're doing is playing with the definite integral that we've got. Now, 1 over u, easy antiderivative. It's ln of absolute value of u, so ftc2 gives us this. Then we can evaluate at those endpoints and we get this. And now we can try to take the limit. So the limit as t approaches 2 from the left of this is going to send you to 0, right? It's going to send you to 0. So as t approaches 2 from the left, this number approaches 0. And so that means that this number is approaching, well, negative infinity, right? Remember, natural log goes to negative infinity as you approach 0. So this is going to approach negative infinity. And so we get positive infinity. Therefore, this integral is divergent. This is not doesn't converge to a finite number. All right. How about this one? So let's see. Think about this one and we'll do this one together too. So start by thinking about it. What do you notice about it first? All right, say out loud what you notice about it. All right, now locate that discontinuity and see what you can do. See if you can split it up, see if your resulting proper integrals are actually finite, or the limit, I should say. See if the limit is actually finite, and then we'll do it together. All right, here we go. Let's do this one together. First thing I notice is that there's an infinite discontinuity at 1, right? This is basically the graph of 1 over x shifted to the right by 1. So there's a big old discontinuity right there at 1. In particular, this graph looks like this. Maybe I'll even just say this, and you got an asymptote right there at 1, right there. So we need to basically split this integral into 2 pieces and then see if any of those pieces are infinite or not. So let's do that. Oh yeah, I forgot to say this first. If you didn't notice that, you might be tempted to simply just apply FTC2 right away and say that this is true. But that's not valid. That's incorrect. It's not a valid use of FTC2. If you go back and you look at the definition of FTC2, or if you look at the statement of the theorem, it says that your function has to be continuous on that interval in order for you to apply FTC2. So take a look at it and you'll see what I mean. So this calculation here, although it seems plausible, is actually totally false. The false step occurs right here. The application of FTC2 is the false step. That's incorrect. It's not valid. You have to split this into 2. You have to take the limit sorry, this should actually say 1. Another typo, my bad. That should say 1 from the left and the right. And if either of those integrals is not finite, then the integral diverges. So here we go. Let's start with one of them. We would like to do this. So we would like to write it like so. So let's try to write it like that, and then let's explore the first integral. Let's explore the integral from 0 to 1. All right, this has an infinite discontinuity at x equals 1, so we need to take the limit as we approach 1 from the left. This is a proper integral. Our function is bounded on that interval. There's no discontinuity there. We can use FTC2. It's continuous there as well. We can use FTC2 and we get this. Boom. Now when we apply those endpoints, we get this. But again, as t goes to 1, t minus 1 is going to go to 0. So natural log is going to go to negative infinity. So this is negative infinity, which means that this integral diverges, and that's all she wrote. That integral diverges, so we're done. That's it. So this one diverges. So we have another divergent integral. Divergent integral. It doesn't mean they will always be divergent, though. That's the interesting thing. Just because these two examples were divergent does not mean they will always be divergent. All right. Now let's get this p-test. This p-test. This one, that's right, that's right. So check out this p-test. This is the p-test when you have a discontinuous integrand. So we're still looking at p integrals. So this is a p integral, but notice now it's not saying that you're going from 1 to infinity. It says you're going from 0 to 1, right? You're going from 0 to 1, and there's a discontinuity at 0. So what's interesting is that the convergence behavior is reversed for these types of integrals. So this integral will be convergent when p is less than 1, and divergent if p is greater than or equal to 1. When p is less than 1, it's going to converge to this number, 1 over 1 minus p. All right? Okay, hold on 1 second. I got to change the lighting back here before it gets too bright. Give me 1 second here. All right, sorry about that. Just noticed it was getting really, really bright behind me, so it kind of messes with the lighting. Not that the lighting's that great, but still. Okay, so this is the result. The convergence relationship is reversed when you have this type of an integral. For the proof, I recommend you try it yourself. So I'm not going to do the proof here. It is similar to the proof of the p-test for type 1 improper integrals. Just split it into those three cases when p is equal to 1 and then when p is less than or greater than 1. But I've got a pretty nice Desmos demonstration here that can give you some intuition for why the convergence changes depending on p. So you can follow along if you'd like. You can just click this link to go to Desmos. I'm going to pull it up right here. Give me 1 second, and then we're going to look at it together. There we go. Okay. So here's the function and the integral that we're looking at. So the function is 1 over x to the p. All right, that's essentially what this curve is that you see right now. This curve, 1 over x to the p. And I'm actually having Desmos compute the value of the integrals for me. So right now, p is equal to 1. And remember, both of these integrals diverged when p was equal to 1. So the integral from, actually, maybe I'll change the order. Here we go. So the integral from 1 to infinity diverges when p is equal to 1. We have 1 over x. Also, the integral from 0 to 1 diverges when p is equal to 1. So the area that we're looking at, or the two separate areas, are the ones over here from 0 to 1, and then the ones from 1 to infinity. All right? But watch this. When I increase p, look how it changes the area. Right? So when p is greater than 1, this integral converges. You see how this is the integral from 1 to infinity? It's literally from this line to infinity. But when p is large, when p is a large number, it flattens out this part of the graph. And so that pinching behavior makes the area finite. So when p is equal to 1, it's basically like saying, hey, oh, come back. There you go, come back. It's saying that this area is not getting pinched fast enough, so the area is infinite. But if you increase that exponent, then the function decreases a lot faster, right? If the exponent down here is large, then the denominators are getting large faster. And so that speed is enough to pinch things off so that you get a finite result. And this is the result you get. So when p is greater than 1, you get that pinching behavior and you get a finite number. And again, as p gets very, very large, the area decreases as well because that pinching is just so rapid that, you know, it falls very quickly. Okay, now let me do the other way. So now let's see what happens. Oh, wait, I was also going to say this. Notice here that on this side, the integral from 0 to 1 diverges. And that makes sense visually, right? Because what's happening here is this area is opening up. This area is opening up. So definitely this is going to diverge. The area is infinite here. This is definitely infinite area, no matter what. And that's because it's literally opening up. as p gets larger. But if p is smaller than 1, check out what happens. So p is equal to 1 right here. Now let's go smaller than 1. Boom. Now we have literally the opposite behavior. So the area between 0 and 1 is now getting pinched. But the area from 1 to infinity is getting widened out. It's getting, or sorry, I should say this way, getting widened out. That's why this one diverges, but now this one converges. So if you integrate from 0 to 1, you're getting convergence when p is small. But if you integrate from 1 to infinity, you're getting divergence when p is small. So it's literally this like reverse behavior, right? Oh, and remember I said that p can be any real number. So even if p is 0, even if p is 0, that behavior still holds, right? Obviously, the area under this infinitely long rectangle is going to be infinite. So that integral is undefined. It's infinite. But the area from 0 to 1 is 1, because now we're just looking at this square. But if p goes below 0, this integral is still finite, because you're just integrating from 0 to 1. So now you're looking at this piece right here. In fact, maybe I can do this real quick. Maybe I can put in a line, x equals 1, but we're going to say 0 less than or equal to y less than or equal to 1. There we go. There we go. So this is kind of like the dividing line. So for this integral, we're only finding the area of this, and that'll be finite. Even if p is large and negative, it'll be finite. But obviously the area from 1 to infinity will be infinite, as you can see right here. So there's the intuition for you. There's the intuition with what's going on right here. Then let me do this for one last note. Again, you can play around with this. I'll save these changes, and I'll change the link in the slides so that you can do this kind of stuff. One thing I wanted to point out was the curve y equals 1 over x. In fact, I'm going to restrict this to be 0 less than x less than infinity. There we go. So the curve 1 over x is basically like the inflection point in some sense. The inflection point in terms of p. So when your function is quite literally 1 over x, you have this blue curve. And in this case, both areas are going to be infinite, and you won't have any convergent integrals. So there's like a change that occurs right when p equals 1. And when p equals 1, you've got the curve 1 over x. So now if I do this, you can see the comparison. See, 1 over x is the blue curve, right? 1 over x is the blue curve. And this is the curve 1 over x to the p. So 1 over x is like an inflection point, literally. It's like where things change in terms of the infinite behavior, the convergence. All right. Okay, so I'll stop playing with that because I could play around with this forever and just think about stuff. So you all can do that on your own time. I encourage you to just play with these things and explore a little bit. But let's get back to the slides. Here we go. Let's get back to the slides and see what's coming next. Because next we have to get a very important test. Let me do this. There we go. Okay. And here's kind of the motivation for this. So the motivation is this. We saw earlier that evaluating an integral, earlier in the course, we saw that evaluating an integral can be difficult and very, very time consuming. So when you're working with improper integrals, it can be really, we'll say, dissatisfying to spend a significant amount of time evaluating an integral only to find that it diverges. You know, what if you go through all of these integration techniques, you know, you converted it to a limit of proper integrals, but you got to do all these techniques. Maybe you've got to do integration by parts, and then maybe a substitution, and then maybe like a trig sub. And then finally you get it to a point where you can take the limit and you find out the limit is infinity. Man, it's dissatisfying, right? It's a bummer. So it would be nice if we had some kind of test or tests that would let us know about the convergence of an integral before we tried to evaluate it. So if we have these tests, it can save us time. The p-tests give us the ability to check for convergence of some particular integrals. So if we've got a p integral, we can tell right away if it's going to converge or not. We just look at that value of p. But what if we don't have a p integral? The p-test doesn't apply unless you have p integrals. So if you don't have a p integral, you can't use the p-test. Now we're going to get a more general test that can help us determine convergence, and this is called the comparison test. The comparison test for integrals. It's a very, very helpful test. So here's what it says. Suppose that f and g are continuous functions on an infinite interval from a to infinity. We're also going to suppose this order relationship of the functions, that g of x and f of x are non-negative on that interval, and that f of x dominates g of x. Okay, that's where that word dominate is happening here. Basically, f of x is above g of x. That's what we're saying. So if you have this order relationship of the functions, then we can get these results. If this integral is convergent, then this integral is convergent too. So in other words, if the integral of f of x converges and g of x is always below f of x, then the integral of g of x has to converge too. And then you get the opposite result if you have divergence. So if this integral is divergent, then this integral must also be divergent. So more specifically, if the integral of g of x diverges and f is always above g, then the integral of f of x has to diverge too, right? I've got a good picture on the next couple slides that gives some intuition for this. But on that note, I want to add this bit at the bottom here. A similar theorem also holds for improper integrals of type 2. So I'm not going to explicitly state it here, but you get the same result with type 2 integrals. All right, but let's look at a picture. Let's look at a picture. I think I have both of them here. I do. Okay, so this picture illustrates the order relationship between our two functions. Here we have f is above g. What this test is saying is this: hey, if the area under the curve of f is finite, then clearly the area under g has to be finite too. Why? Because f is always above g. So if the area under f is a finite number, then this area must also be a finite number. So there's like that dominating relationship is important. All right, that's this is saying. So if the area under f is finite, then the area under G has to be finite. That's what it's saying. All right, now let's look at the other result. So now the opposite result is also true. If the area under G is infinite, then the area under F must also be infinite, because the area under G is already infinite and F is always above G. So the area under F is going to be infinite too. That's what this is saying. So if this area is infinite, then this area is infinite. Makes sense, right? It makes sense intuitively. And when you look at the geometry, one note, do I say it here? Yeah, okay, one note here. I want to point out explicitly that we are comparing integrands to get convergence information about their integrals. So we are not starting by comparing the two integrals. We don't know anything about the two integrals. We don't know about the integral of f. We don't know about the integral of g outright. What we know is the order relationship between our two functions. Then this is saying if you have that order relationship and you know something about the integral of one of them, that can tell you about the integral of the other. All right, so that's very, very important point to make. You're comparing the functions to get information about their integrals. All right. Another thing that I like to say is you shouldn't try to memorize f and g and f is above g or g is below f. You don't want to think of it like that. You want to just try to figure out what the domination relationship is. Here, f is dominating g. So f is always above g. So if g, the integral of g blows up, the integral of f blows up too. But if the integral of f is finite, then the integral of g is finite. That's the idea. So I'm going to throw the thinker up for a minute, and I want you to just ponder this. Just ponder this idea for a few minutes. All right, now let's move forward. with this helpful comparison. So why is this test so helpful, or why is this test so nice? Because it basically tells you, hey, if you know a little bit about a function's improper integral, you might be able to tell if another integral converges or not. And one thing that can help with comparisons is knowing how one integral behaves. So here, this is a result that a student asked me about a couple semesters ago, and I decided to prove it because they wanted to be able to compare integrals that had these functions in them. So this is a relationship between functions that look like e to the mx and, or sorry, 1 over e to the mx and 1 over x to the n. So if you want to know the dominating relationship, this is what it is. So for all x greater than or equal to 1 and any real numbers, positive real numbers m and n, if this ratio n over m is less than e, then you get this dominating relationship that this p function is greater than this exponential function. That's basically it. So maybe this is something that you want to investigate, but you would like to compare it to a p integral. This tells you how you can do it. This is how it works, all right? So here's the proof. The proof is actually not so bad. It's kind of a cute proof. So here it is. Suppose that n over m is less than e. Well, the function x over ln of x has a minimum at the point e comma e. How did this come about? Well, I reverse engineered it to get this result. So basically I started with this and went backward and then found the constraints, all right? So this function has a minimum at these points. So if this ratio is less than e, then we know that n over m has to be less than all the values of this function for x bigger than or equal to 1, right? So the minimum of this is e for all x greater than 1, all right? Okay, now you just do some clever algebra, multiply both sides by m, exponentiate both sides with a base of e, and then here's that little clever trick, right? This is rewriting any exponential with a base of e. It's using that technique right here. So this is just x to the n. This is e to the mx still. Then when you reciprocate, you get this. Or when you cross multiply, you get this. Boom, there's the result. Long story short, if you've got an integrand that looks like this, you might be able to compare it, or you can compare it to a p integral. And this is the comparison right there. You just need to know that this is true. You just need to know if this is true. All right, let's try to use it. So we're gonna do a couple examples here. So I know this is a bit of another long lecture, but it's good to make sense of this stuff because it will help you prepare for chapter 11. So I'm going to explicitly say this: without evaluating the integral directly, determine if this converges or diverges, all right? So think about this one for a minute and see if you can find a good comparison that will help you determine convergence. All right, now say something out loud to yourself. Maybe what's an integral that you think you could compare it to? All right, now try to work on it on your own. See if you can determine if it converges or diverges. Remember, you are not evaluating the integral. You are just determining if it converges. So don't try to evaluate it. Use the comparison theorem. All right, now let's do it to, wrong button. There we go. Still the wrong button. There it is. Now let's do it together. Okay, so one thing to keep in mind is that, remember, we really love functions like sine and cosine and arctangent because they're bounded, and they're bounded over the entire real line. So in particular, sine squared is always less than or equal to 1. So consequently, sine squared over x squared is less than or equal to 1 over x squared. This is the integrand that we're interested in. This is an integrand that we know about because this is the integrand of a p integral. So by the p test, we know that this integral converges because p is greater than 1. So we have an order relationship this function dominates this function, and the integral of this function converges. So by the comparison test, the integral of this function must also converge, and that is the result. That's the conclusion. All right, so think about that argument for just a minute again, all right? Ponder it for a minute, and we're going to do another example. All right, let's try this again. So once again, without evaluating the integral, do not try to evaluate the integral. Some of these integrals you cannot even evaluate using FTC2. So do not evaluate the integral. See if you can determine if this thing converges or diverges. Think about it on your own for a minute. Now say something out loud to your dog or your wall or your bed or whatever about what you would do first. Now try to work it out on your own. So find a good comparison. Is there anything you could compare that to? And now let's work on it together. All right. Well, there's one thing I noticed right away, and it's something that I mentioned literally in the last example. We've got arctangent up here. We love arctangent. Arctangent's a great function. It's bounded. It's bounded over the entire real line. This function doesn't go very far up or down. In fact, it's bounded between negative pi over 2 and pi over 2. So what's happening now is we're taking a bounded number and dividing it by an ever-increasing number. Seems like it might converge. It might converge, we just have to get a proper comparison. So here we go. Let's see. Oh, another thing I should point out, I forgot to mention. Notice this integral doesn't start at 1. It starts at 0. So technically we can't use anything like the p-test yet because it's got to start at 1. So the first thing we need to do is we need to rewrite this integral as two separate integrals, an integral from 0 to 1 and an integral from 1 to infinity. Now the first integral here, this first integral is finite. It's a finite number. This is a definite integral. Our integrand is bounded on that interval. So whatever this thing is, it's just a number. It's just a number, so it does not affect convergence whatsoever. This has no effect on convergence. The thing that will change convergence is this piece. That piece is the thing that affects convergence. That's the piece that we need to explore. So, like I'd said a minute ago, arctangent is bounded above by pi over 2. So in particular, we get this inequality right here, right? This is less than pi over 2. So this is less than pi over 2 divided by 2 plus e to the x. Now, another thing to notice, 2 plus e to the x is always greater than e to the x. So this fraction is always less than this fraction, okay? Now, we can rewrite it like this. So one thing I want to mention here is all I'm trying to do is set up a helpful comparison. I'm trying to just set up a comparison between integrands that I'm trying to set up a comparison of this integrand with another one that I might know about. That's really what you're trying to do here. I want to compare it to something that I know about, because that way maybe I can determine what this thing is doing, what that function's doing, what that integral's doing, and so on. So this is the integral we have to consider, because we basically got this to compare to this, right? So this is the new integral that we need to explore. If we can determine if that integral converges or not, then we can use it to do a comparison. Well, our helpful comparison, that nifty inequality that I just told you about, that can help here, because here 2 is n and 1 is m. And we know that 2 over 1 is less than e. So now we know that this has to be true. This has to be true. That's just using that inequality from that previous theorem. Now we know that this integral converges by the p-test. We know that converges by the p-test. So by the comparison test, this integral converges as well, because this function is dominated by this function. The integral of this function converges, so the integral of this function converges by the comparison test. That means we know this integral converges. Therefore, this integral here converges, again by the comparison test, using this comparison. Thus, this integral has to converge as well. And that was the original integral we started with. All right, so this is another one where I want to throw up the thinker again, and I want you to just kind of ponder this argument for a minute. So think about the argument that was made, reread these slides, and see where each piece came into play. All right, now let's do one more example. Again, without evaluating the integral directly, do not try to evaluate it directly. Just determine if this converges or diverges. Try to do this one on your own and try to write out your argument. Try to write out exactly what you're arguing. There we go. Think about what comparison you could make. Anything jump out? All right, now say out loud what comparison you could make to anybody, your sister, your brother, your dog, the wall. Go. Okay, now try to work it out. Try to write down what your argument is. What is your comparison, and how can you use the comparison test to get a conclusion? Okay, now let's do it together. Let's see. The first thing that jumps out to me is this x in the denominator. And so what I see here is I basically see something over x. So I feel like maybe I could compare this to the function 1 over x. And then if I can compare it to the function 1 over x, I could think about the integral of 1 over x, because I know what that integral does, because that's a p integral. So here we go. Yes, so what I notice here is that this integrand is always bigger, or should say this function, is always strictly greater than 1 over x. And that makes sense because e to the negative x is always a positive number, right? E to the negative x, it's an exponential, it's always positive. So if I take 1 and I add a positive number to it, that's always going to be bigger than 1. Definitely going to be bigger than 1. So this thing is bigger than this thing. But I know about the integral of this function. The integral from 1 to infinity of 1 over x diverges by the p-test, because here p is equal to 1. So that diverges by the p-test. Well, this function is always greater than this function, and the integral of this function diverges. So the integral of this function must also diverge by the comparison test. And that's the result, right? That's the argument. That's how the argument goes. Okay. All right, so a lot of details here, a lot of stuff going on. Just to finish things up here, again, I know this is a bit long. I want to give you these notes to carry with you now and to help you prepare for Chapter 11, because Chapter 11 can be a bit of a shock to a lot of students that are first learning how to do that stuff. The format of these 3 previous examples is that of a proof. So what we did was we proved a result about those integrals. We were proving if an integral converges or diverges using inequality relationships and theorems that we have already established. This type of reasoning is exactly what Chapter 11 is like. So when we get to Chapter 11, we're going to be working with sequences and series, and the main question we have is, do they converge or do they diverge? That's pretty much it. How do you establish convergence or divergence? You basically use all of these theorems that we'll develop. So in that chapter, we're going to establish a couple dozen theorems that we can use to determine if a series converges or diverges. So when you get into that chapter, your work for those problems is going to look a lot like the work that we just did on these previous examples. That's what it's going to look like. So a couple of notes. One, it is wise to get comfortable with this now. Practice writing your reasoning using complete sentences. Do it now, start it now, so that it's not so hard to adapt when you get to Chapter 11. Just use complete sentences. Write out the sentences. This thing is less than this, therefore blah, 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 comparison test, and so on. Practice that now so that it's easier later. Moreover, this is a more important point, or maybe a more important point, determining what a series converges to can be extremely difficult, if not impossible. There are many examples of series that we knew converged for decades, but it took, 70 to 80 years for somebody to prove what it converged to. So generally speaking, it can be really difficult to find what a series converges to. We just need to know if it converges at all. That's really what we're looking for. And we won't be able to simply evaluate a series because we don't have fundamental theorem of calculus for series. That only applies to integrals. So there's no like way around using the theorems or the comparison test. Like you have no other choice. So it's good to get comfortable with it now. Um, in other words, yeah, there you go. You're going to be required to make arguments like those that we saw in the previous problems when we get to chapter 11. And there won't be any other way of doing it. Like you have to use that type of method. All right. Okay, we can talk more about that tomorrow, but now let's play. All right, so we'll do the activity for this in activity the next time we see each other. I won't ramble too much longer. If you've got questions, please ask. Thank you again for bearing with me, and I'll see you all next time.